Hello friends, in this video we're going to prove Rodrigue's formula. This is the formula, okay, and where Pn of x is Legendre's polynomial, okay. So before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel, okay. And if you want to follow me on Insta, this is my Insta ID, OJHALAKHYAJIT123. That's my Insta ID. You can follow me on Insta. So now let's start. So here is the Rodrigue's formula. Okay, Pn of x is equal to 1 by 2 to the power n in factorial n, nth order derivative of x square minus 1 whole to the power n with respect to x. This is the formula. So let me prove this formula. Okay, so proof. So to prove this formula, let me consider, let v is equal to x square minus 1 whole to the power n. Let me consider this is equal to v, and let me give it suppose equation number 1. Okay, so now if we differentiate both sides with respect to x, then what we're gonna have, if we differentiate it with respect to x, ddx of v, so then what we're gonna have here. Okay, so if you differentiate this power should be written first, and then x square minus 1 whole to the power, this power will be reduced by 1, so that is whole to the power n minus 1. Then we have to differentiate this term which is within the bracket, that's going to be equal to 2 into x, right? So hope you have understood this. So now let me do one thing, just let me write this one here. Okay, so now let us multiply x minus 1 both sides. Okay, so to make it to make this power n, let me multiply x minus 1 both sides. First let me copy the same step. Okay. So let's multiply x square minus 1 on both sides, then what we're gonna have, let's multiply x square minus 1 on this side as well as this side, x square minus 1. Okay, let us multiply this term on both sides. So now you see, if you multiply this one and this one, then here this power will be n. Okay, because here we have power 1, so 1 plus n minus 1, that's gonna be n. So on the right hand side we're gonna have n into x square minus 1 whole to the power n. Okay, so hope you have understood this. So when we have multiplied x square minus 1 on both sides of this equation, of this above equation, then we have got this equation, right? Hope you have understood this. So now just give me a second. Okay, let me rearrange this step. So what we have done, multiplying both sides, of the above equation by x square minus 1. Okay, that's what we have done. Okay, now you see what we can do. Okay, here from equation number 1, this part can be replaced by v. Okay, then this equation becomes of this form, x square minus derivative of v with respect to x is equal to n v into twice x, or you can write this way, 2 n vx, right? You can write this way. So using equation number 1. Okay, so now let me take this one as equation number 2. Let me consider this is as equation number 2. So let it be equation number 2. right? Now differentiating equation number 2. Now differentiating equation number 2. Let me write it properly. With respect to x, n minus 1 times, and to differentiate this equation number 2, n minus 1 times, we must use Leibniz theorem. Okay, using Leibniz theorem. I'm gonna write the theorem, don't worry. Leibniz theorem. Sorry. So what was the theorem? Okay, so let me write here Leibniz theorem. Okay, let me write here. Okay, just give me a second. So Leibniz theorem. Now you see, suppose we need to differentiate product of two functions u into v, but now we need to differentiate n times, right? So then what happens? Okay, according to this theorem, nc0, okay, c for combination here, and nth order derivative of first function. So here this doesn't mean that u to the power n, that means you have to multiply u n number of times. So here I am writing u to the power n to represent derivative of u n times. Okay, nth order derivative of u, then v to the power 0, that means 0th order derivative of v, that means there is no derivation of the v, right? That's it. Then next term will be nc2. Then here we had taken nth order derivative. Now we need to take n minus 1 order, that means now this order will be reduced by 1. Derivative of, we have to differentiate u now 1 time less. Okay, so now we're going to write u n minus 1 order derivative of u. So here n minus 1, then first order derivative of v, plus then nc3, then the order of the derivative of u, that will be decreasing, okay, in its step u. Here n plus, sorry, not plus, n minus 2 now. Okay, then second order derivative of v. So v is, this is not v square, okay, this is second order derivative of v. Okay, plus dot dot dot, so on. That's how so that's the Leibniz theorem. Okay, so hope you have understood this. Now you see, if we use that formula here in equation number 2, okay, then what we're gonna have, and here we're gonna take this dv dx, we're gonna take this one as u, and we're gonna take this x square minus 1 as v. Okay, now let me differentiate it n minus 1 times. Now here you see, now let me copy this equation number 2 and let me differentiate it with respect to x n plus 1 times. Okay, let me go to the now here you see, differentiating this equation number 2 both sides n plus 1 times. I have got this result. I have already written here. Now let me explain how I have got this. So I have applied the Leibniz theorem, as I have already written this equation in previous slide here, you see. So you don't need to repeat this equation again, okay, once you have written. So as I have changed the slide, so I have written it again. Okay, now you see how to apply the Leibniz theorem. So here you see, let me show you. so we are going to differentiate n plus 1 times, right? So now Leibniz theorem is this. Here you see, suppose we have u into v and we need to differentiate it n times. If we need to differentiate it n times, okay, ddx here, okay, suppose we need to differentiate it n times. Let me write the differential coefficient properly. So it is nth order derivative, okay. Then first we're going to write nc0, which is equal to 1, so we don't need to mention this. Then nth order derivative of u into v, okay. Then nc2, here it was nc1, and sorry, nc0, not 1, here it's supposed to be nc1, okay. So nc0 is equal to 1, that's why we don't used to write this nc0, okay. C4, now you have already got, I think, permutation and combination. nc1 means factorial n divided by 1 factorial n minus 1 factorial, right? This is the formula. If you have r here, then you need to write here r instead of 1, okay. That's it. So now you see, then you have to reduce this order of derivative in the next term, that is n minus 1 order derivative x to the power n minus 1. Okay. Sorry, here actually it doesn't mean x to the power n, this is the order of derivative, okay. So now let us differentiate u with respect to x n minus 1 times. Then differentiate v, take the first order derivative of v. Then in the next term, order of the derivative of u will be reduced, and order of the derivative of v, that will be raised by 1 in each and every step. So nc2, so now n minus 2 is the order of this derivative of u now with respect to x. Then raise the order of this derivative of v by 1 again, that is second order derivative. That's how we used to continue to do that. So here you see, in this case we have taken this dv by dx as u, and this one is taken as v, okay. This one is taken as u. So now here you see, as we have this, we have taken this as u and x square minus 1 as v. Now according to this formula, first term should be nc0, that's going to be equal to 1. Simply let me write 1 into, here we are differentiating n plus 1 times, right? N plus 1 times, so we need to differentiate it n plus 1 time, n plus 1, n plus 1. So here we have already first order derivative, right? So we need to differentiate it n plus 1 times, so dv dx, and in the first term we don't use to differentiate this v, right? Here v is taken as x square minus 1. So here you see, here we have already first order derivative. Then if we differentiate it again n plus 1 times, then we should get this n plus 2 order derivative. Here the order of the derivative should be n plus 2, as it is already first order derivative, right? So this term is written here, okay. Hope you have understood this. In the second term, what we should get according to this formula, so now reduce this order of derivative by 1. So here the order of derivative is reduced by 1. Here it was n plus 2, now it is n plus 1. And here we had nc0, here n plus 1 actually, in this case, as we are differentiating n plus 1. So n plus 1 c0 is equal to 1, so that's why, so n plus 1 c0 is not mentioned here. Here it's supposed to be n plus 1 c0, which is equal to 1, that's why I haven't mentioned that. And here you see, Then here you see, now we have reduced the derivative of order of the derivative of v by 1, and we need to take the first order derivative of v. Here v is taken is this one. So now you see, as we are differentiating with respect to x, as we are differentiating this with respect to x n plus 1 times, so that's right. So here we have taken the derivative n plus derivative of order n plus 2, derivative of v of order n plus 2, and we haven't differentiated this term initially. Then in the next term we should take the first order derivative of this, and we need to take the n plus 1 order derivative of this term, right? And in the next term we should raise the order of derivative of this term. Then in the next term we're going to take the second order derivative of this part, and nth order derivative of v, okay, right, as this. Okay, now here you see, let me clean this part. Okay, so here you see, let me tell you, don't compare this v with this v that I have written in this formula, because I have considered that this part del v by del x as u. I have considered that part as u, and I have considered v as this part. This, in this formula, this v represents here, represents this x square minus 1 in this case. So here you see, here we have taken v simply without any differentiation. Here we have taken first order derivative of v, and here we have taken second order derivative of v. So similarly, here we have taken this x square minus 1, then first order derivative of x square minus 1, that gives twice x. If you take the first order derivative of x square minus 1, then it gives twice x, right? Similarly, in the next term we should take the second order derivative of that. So if we take the second order derivative, if you differentiate it again, then it will give 2, right? And third term will be 0, because if you differentiate this 2 again, that's gonna give you 0, because it is constant term. So that's why we can end it here. Okay, understood? And in the next part, right hand side, let me clean these things. Okay, just give me a... Okay, now you see, right hand side, if you differentiate 2n vx n plus 1 times, n plus 1 times, okay, if you take the derivative of this part of order n plus 1, then what happens here? Here also we're going to apply the same formula, Leibniz theorem, right? So first let me clean this. Okay, then here what I have done here, this part is constant, which is taken outside, right? And again here we have considered that this v as u, as I have used in this formula, and I have taken x as v in this formula, right? So that means here it should give twice n. First we're gonna differentiate v how many times? N plus 1 times with respect to x, then multiply it by x. Okay, then what we're gonna do, then we're gonna reduce this order of derivative of v, okay, twice n, then reduce the order of derivative of v by 1, that is, here we're gonna write nth order derivative with respect to x, right? Then we need to take the first order derivative of x, that is ddx of x, that's gonna give you 1, right? Simply 1. In the next term we should take twice n, then reduce the order of derivative, that is dn minus 1 here, and dx n minus 1 of v, then we need to differentiate this again, that's gonna give you 0. So that means if you continue, then you will get 0. Okay, so only we have got two terms here, and from here we have taken this twice n common. Okay, so that's why we have got this. And one more thing here, I have forgot to mention here, this n plus 1 c1. Okay, so n plus 1 c0 is 0, sorry 1, that's why here we don't use to mention that. Hope you have understood this. So that's how we have got this. Okay, so now just give me a second. So now, as I have written this equation number 2 in previous slide already, so let me clean this part. Okay, so now here let me simplify this. What I'm going to do here, first let me write this one as it is, x square minus 1, just give me a second, x square minus 1 into derivative of v, and order of the derivative is n plus 2 here, by dx. Okay, then plus, so what we can do now, you bring this term to this side. Okay, then this, there will be negative sign. If you write this equal sign here, and if you transfer this one on this side of the equal sign, there will be minus, right? Hope you have understood this. Okay, that means if you bring this one to this side of the equal sign, then what we're gonna have negative sign before this term. And then what we can do, we can take this part common. Here you can see this part can be taken common. Okay, and doing so, what we're going to do, what we're going to have, here you see, we're going to have x, n, as we don't have any n in this term, so here we're going to have minus n. When this term will be brought to this side, then it will be negative. After that we are taking common, n plus 1 v, right? So hope you have understood this. Similarly, we can take this part common from these two terms, right? And on taking common, so if you bring this term to this side of the right hand side, this side of the equal sign, then this minus sign will be this plus sign will be negative on this side, on the left hand side, right? And then we can take this part common, right? So then what we're going to have here, plus 2 into, because we have 2n here. Okay, so this 2 is taken common, 2 into, within bracket we're going to have n plus 1 c2 minus, here n should be written into this n plus 1 c1, right? Then nth order derivative of v with respect to x. Sorry, let me write it properly. Nth order derivative of v with respect to x, which is equal to 0 here. Okay, so hope you have understood what we have done. We have transferred this term to the left hand side, and then we have simplified, taken common what are the terms can be taken common, and then we have got right hand side 0, right? So now let me take a new slide to simplify this. Okay, let me copy this last step and let me go to a new slide. Okay, here is the new slide. So now what we can do here, okay, now you see, first let me simplify this part. So n plus 1 c1 minus n, right? Okay, then here you see this is actually equal to 1. Let me show you how. nc1, we know that ncr is equal to factorial n divided by factorial r into n minus r factorial. So if we apply that, so here we're gonna have n plus 1 factorial by 1 factorial into n plus 1 minus 1 factorial. Here we have minus n, then n plus 1 factorial. 1 factorial is simply 1, then here plus 1 minus 1 gone, then we have n factorial. So now you see n plus 1 factorial means n plus 1 into n factorial, you can write that way. Then we have n factorial here minus n, so n factorial gone, so you're gonna have n plus 1 minus n, that's gonna be equal to 1. So this part is equal to 1, right? So we have got this part is equal to 1. Now let me simplify this part. Okay, now let me clean this, pause the video and note these things. Then n plus 1 c2 minus n into n plus 1 c2. You don't need to show these calculations, but to understand, please note this. Okay. Sorry, it's supposed to be 1. Okay. So now what happens here? Again, if you apply this formula NCR, that is factorial n by factorial r into n minus r factorial, if we apply that here, then what we're going to have, n plus 1 factorial by 2 factorial into n plus 1 minus 2 factorial. Okay, then minus n into, if you apply this formula here also, then what we're going to have, n plus 1 factorial divided by factorial 1 into n plus 1 minus 1 factorial. Okay, so then here you see this n plus 1 minus 2 is nothing but n minus 1. This is nothing but n minus 1, right? And here also this plus 1 minus 1 gone, so it is simply factorial n. So it is simply factorial n. And factorial 1 is 1, so simply we can write factorial n only. And factorial 2 here, factorial 2 is 2 into 1, that means simply you can write 2. Now you see this factorial n plus 1 can be written this way, n plus 1 into n minus 1 factorial, right? Similarly, n plus 1 factorial, here it can be written this way, n plus 1 into n factorial, right? So n factorial gone, so here n minus 1 factorial gone. So what we have is n plus 1 by into 2 by, sorry, n plus 1 into n by 2, then minus n into n plus 1. That is what we have now. So if you take LCM and if you simplify this, then you're gonna have n into n plus 1. This n plus 1 into n means n into n plus 1, same thing, minus 2 into n plus 1 divided by 2. That means here you see, if you subtract these two, you're gonna have minus n into n plus 1, then we have divided by 2. That's what we have got. Okay, this is equal to this. This is what we have got. Now let me clean this thing. So now you see, so what we can do here, so here this part is equal to minus n into n plus 1 divided by 2. If you multiply these two here, these two cancels, right? So hope you have understood this. And then what we're gonna have, so we're gonna end up getting this x square minus 1, then derivative of v, how many times differentiation, how many times, what is the order of derivative, n plus 2, right? Then plus twice x, this part become 1, so simply you can write twice x, then n plus 1 order derivative of v, right? Then plus, so these two cancels, so we have got minus n into n plus 1. So instead of this part, if you put this value, then these two will cancel, right? Hope you have understood this. So we're gonna have n minus 1 into n plus 1, sorry, minus n into n plus 1, right? That's it. So hope you have understood this. Now let me clean these things. So nth order derivative of v with respect to x equal to 0. This is what we have got, right? So now let me write this equation and let me go to a new slide. Pause the video and note it. Okay, so here is the equation. Now you see, if we multiply each and every term by minus 1, if we multiply minus 1 here, multiply minus 1 here, here also multiply minus 1, then what we're gonna have? Then we're gonna have this x square minus 1 will be 1 minus x square into n plus 2 order derivative of v. It is minus twice x as it is multiplied by minus 1. Then n plus 1 order derivative of v with respect to x. Then it's gonna be plus as it is multiplied by minus 1. So n into n plus 1 nth order derivative of v, nth order derivative of v with respect to x is equal to 0. So this is what we have got, right? Now you see, let us consider y is equal to nth order derivative of v with respect to x. Okay, then this can be written as second order derivative. So second order derivative of v with respect to x, right? Because we have taken nth order derivative of v with respect to x as y, so this can be replaced by second order derivative of y with respect to x, right? Because here order is n plus 2, right? Hope you have understood this. So let me write, let that nth order derivative of v with respect to x is suppose y. Therefore this equation can be written as 1 minus x square. So here the order is n plus 2 and we have taken on nth order is nth order of the nth order derivative of v is y, so that's why we can replace it by second order derivative of y with respect to x minus twice x. Then here order is n plus 1, so we can write first order derivative of y with respect to x, then plus n into n plus 1, then y is equal to 0, right? So this is Legendre's differential equation. Legendre's differential equation, right? So now let me copy this equation and let me go to the next slide. So here is the new slide. So let me paste the last step here. Okay, this was the equation. So now you see, we know that Legendre polynomial is a solution of this Legendre's equation. So we can write, you see, as we have considered y is equal to this nth order derivative of v, right? That must be also a solution of this. So what we can write, that we can write that this Pn of x, which must be some constant into, which must be equal to some constant into del v by nth order derivative of v with respect to x is a solution of the Legendre's or of the above equation. We can write this way, right? We can mention one more thing here. as y is equal to nth order derivative of v with respect to x. So here we have y, so this must be a solution, and we know this Legendre polynomial Pn of x is also a solution of the above equation. Therefore we can write this way. Okay, so hope you have understood this. So let me consider this is equation number 4. Let me consider this is suppose equation number 4, and let me consider this one as equation number 3. This one as equation number 3. Okay, hope you have understood this. Okay, now you see our aim is to determine this value of c, right? Value of c, this constant c. So let me write it properly, where c is a constant, right? C is a constant. Now how to determine that? Now you see from equation number 1 we have considered that v is equal to x square plus 1 x square plus 1 whole to the power n. This is equal to v. We have considered this one, right? From equation number 1. Let me go back to the previous slides. Where is the first slide? Here, this is the equation number 1, right? So now you see so it can be written this way. Now x square minus 1, it can be considered as x square minus 1 square, that is equal to x plus 1 into x minus 1, a plus b into a minus b formula, right? X plus 1 into x minus 1. So then here we can write x plus 1 whole to the power n into x minus 1 whole to the power n, x minus 1 whole to the power n. We can write this way, right? So now you see, if we differentiate n times, if we differentiate n times v, if we differentiate v n times, right, with respect to x, then what we're going to have? Again we're going to apply the Leibniz theorem. So how to apply that? nc0, that's going to be equal to 1, so we don't use to write that. Then let me consider this one as v and this one as u. Okay, let me write this one here. Okay, now you see, so first we're going to take nth order derivative of x minus 1 whole to the power n with respect to x into x plus 1 whole to the power n. Then we're going to take then according to Leibniz theorem, then we should have nc1. Then this order of derivative should be reduced, then n minus 1 here, order of the derivative is now n minus 1, and derivative of x minus 1 whole to the power n. Then we have to differentiate this. We need to take the first order derivative of x plus 1 whole to the power n plus dot dot dot, so on. That's how we're gonna continue, right? So let me copy this last term and let me go to a new slide, as we have not enough space here. Okay, let me write here. So this is what we have got. Okay, so if you continue this, then you should get if you see, this order is going to be reduced in each and every term. Okay, okay, so we have to take the descending order of the derivative. So at the end we should get zeroth order derivative. That means simply this term, if you write this term without differential coefficient, x minus 1 n, and here it becomes here you see order of this derivative becomes nth order. Okay, x plus 1. That means in Leibniz theorem, the term here you see which one is started with nth order into v, at the end it will be 0. Here the order of the derivative here 0. That means we have not taken here differential equation. Then this term gonna be v to the power n, means that means like this. Here we have taken nth order derivative of u, then into v, and it should be ended with u into nth order derivative of v, u into nth order derivative of v. So we do have the coefficients, though I am not writing here. So hope you have understood this, right? And at the end the coefficients, this this one will be ncn, which is again 1, right? ncn is also 1. So that's why I am not writing here. So now you see, for x is equal to 1, if we take x is equal to 1, okay, let me do one more thing. Let me show you one more thing. Suppose you have x plus 1 or x minus 1 whole to the power 3. Okay, so let me show you something. So if you differentiate it once, then what you should get? You should get 3 x minus 1 whole to the power 2, right? Again, if you differentiate it, then you're gonna get 1, which is within bracket. If you differentiate the term which is within bracket, okay, then you're gonna get 1. Now again, if you differentiate it again, then what you're gonna have? 3 into 2 into x minus 1, right? When you differentiate it again, that means if you take the third order derivative of this x minus 1 whole to the power 3, then what you're gonna have? 3 into 2 into 1. If you differentiate this term again, then you're gonna get 1, right? So now you see here the order of derivative and the power is same. In that case, this term is not exist here, right? Okay, but if you differentiate it if you take the second order derivative, that means if you take the order of the derivative less than this power, then its result contain x minus 2, x minus 1, right? So now in this case, you see this order of derivative and power, that's same. So that's why if you differentiate it n times, then you're gonna get n into n minus 1 into ... so on, and at the end you're gonna get 1, but that result will not contain x minus 1. Okay, so that's why on putting x is equal to 1, if you put here x is equal to 1, then it's gonna be 2 to the power n. So here nth order derivative of v with respect to x, you're gonna get 2 to the power n, and from this part you're gonna get n into n minus 1 into n minus 2 into ... so on into 1, which is equal to factorial n, right? As you have got here, you see this is equal to factorial 3. If you take the fourth order derivative with respect to x of x to the power 4, x minus 1 whole to the power 4, then you're gonna get 4 into 3 into 2 into 1, that's gonna be factorial 4, right? So here we have nth order derivative and power is n here, so that's why we're gonna get factorial n. So putting x is equal to 1, we're gonna get here 2 to the power n into factorial n, and remaining terms will be 0, because here you see this is the power, and this power is n here, and the order of derivative is 1 less. So at the end here, what you're gonna have here, you're gonna have n into n minus 1 into dot dot dot, and here it will contain 1 x minus 1 term. Okay, on putting 1, it will be on putting x is equal to 1, that will be equal to 0, right? So if you see, so excluding this the first term, except this first term, all the remaining terms will contain this x minus 1. Okay, so all the remaining terms will contain x minus 1, so that's why remaining part will be equal to 0. So here we can write that since all the other terms disappear as x minus 1 is a factor in every term, except the first term. So that's why we have got this result. Okay, hope you have understood this. Now you see, okay, now from equation number 4, what was the equation number 4? Let me go back to the equation number 4, this one, equation number 4. Now let me copy this equation. Okay, here you see, this is equation number 4. For x is equal to 1, this equation becomes, this equation number 4 will be Pn of 1 is equal to c into, and we have got this is equal to this one, right? That is 2 to the power n factorial n. Okay, for x is equal to 1. Now remember one thing, Pn of 1 is equal to 1. Okay, why it is 1, we're gonna discuss in the next video. Okay, because that's gonna be very long. Okay, to prove that actually here we have considered that this result is known to us, that Pn of 1 is equal to 1. Here just for the time being, you just remember this. So when we will discuss generating function of Legendre's polynomial, then we're going to discuss about this value Pn of 1 is equal to 1, why it is 1. Okay, so here we're going to consider this is known to us. Okay, so that's why from here you see what we have got, c into 2 to the power n factorial n is equal to 1, since Pn of 1 is equal to 1. So here, now let me copy this last step and let me go to the next slide. So here what we have got c is equal to this, so that's why c gonna be equal to, we have got c into 2 to the power n into factorial n is equal to 1, so c will be 1 by 2 to the power n into factorial n. Okay, that's what we have got. This is the value of c. Now using this value, let me consider this is equation number 5. So what was the equation number 4? Let me go back to the previous slide. This was the equation number 4. So let me copy this equation. Here you see. So this was equation number 4. Now use 5 in equation number 4. This was equation number 4. So using 5 in 4, if you use this value of c here, then Pn of x, let me write it properly, Pn of x, that's going to be equal to, instead of c we're going to put 2 to the power n factorial n, nth order derivative of v with respect to x, and we know that v is equal to x to the power n, x to the power 2, that means x square minus 1 whole to the power n. So we're going to put that value as well. So what we can write, therefore we can write, that was equation number 1 actually. V is equal to x square minus 1 whole to the power n. That was equation number 1 if you check the first slide. Okay, so now you see Pn of x is equal to 1 by 2 to the power n factorial n, nth order derivative of v. Instead of v we're going to write x square minus 1 whole to the power n. So this is the required formula that we wanted to prove. Okay, Rodrigue's formula. So which is proved, right? So hope you have understood this. So in the next video we're going to discuss about generating function of Legendre's polynomial, and you see, and in that video I'm going to show you how Pn of Pn of 1 is equal to 1. I'm going to show you that as well. So in the next video, so stay connected. See you in the next video. Bye bye.